Hello. So in this unit, we're going to continue with our move into continuous time models and models that have continuous densities over the parameter space. So last time we talked about gradient flow, which is a deterministic differential equation. Now we're going to move to what's called stochastic differential equations. So it's still continuous time, but it's a differential equation that is stochastic. It allows the future to be not determined by the present. So again, the fundamental idea here is that we sort of believe that in practice, we get this kind of stationary distribution effect. And what we're going to do with the stochastic differential equations is get a mathematical model that gives us a somewhat clearer, more intuitive understanding of things like temperature. And we're going to be able to solve for stationary densities under these stochastic differential equation models. And there's a fundamental question, a fundamental intuition. So when we go to a stochastic process with a stationary distribution, many of you are probably familiar with MCMC methods. And MCMC methods are typically designed to have what's called a Gibbs stationary distribution. So when you do the Metropolis algorithm or Gibbs sampling, you design a process whose stationary distribution is this Gibbs distribution. And a natural question to ask is it true that if we formulate or try to understand SGD as a stochastic process with a stationary distribution, is it converging on the Gibbs distribution, which we are most familiar with in other stochastic processes? So to do this, we're going to move to these stochastic differential equations, and some special cases of this are Brownian motion and something called Langevin dynamics. Brownian motion, I think, was first well formulated by Einstein. Langevin dynamics is the special case where the stationary distribution is Gibbs. And what we're going to show here later is that for the stochastic differential equations that correspond to SGD, typically the stationary distributions are not Gibbs. And it'll be important to understand that, and that'll have implications. Okay, so remember that in gradient flow, we explicitly considered a limit where the learning rate is going to 0. So if you take the learning rate to 0, you get gradient flow. What we're going to do now is hold the learning rate fixed. Okay, so we're looking at the standard SGD equation, discrete updates, but we're holding this fixed, and we're still going to define time to be the sum of the learning rates. So there's still going to be a continuous notion of time, and we're going to think of the case where eta is fixed but small. And we're still going to be thinking in terms of n steps, where we define delta t to be over n steps of this to be n times the learning rate. Now we want to consider delta t to be large enough. We will want to consider delta t to be large enough so that delta t corresponds to a large n. We're going to be averaging over a large set of updates. And that's so that we get statistics that are going to be meaningful for our stochastic differential equation. But we also want delta t to be small enough so that the gradient distribution, the distribution of gradient estimates, the statistics of the gradient estimates do not change much over the interval. So we're looking at this range of possible delta t's. So what I'm going to do is I'm just going to write out what happens at t plus delta t under ordinary stochastic gradient descent with a fixed learning rate. So if we take an interval delta t, the next value of the parameter vector is its original value at time t minus the true gradient times delta t. So that sort of corresponds to gradient flow. But then what I've done is I've taken the gradient estimates and I've added and subtracted the true gradient. So I get a true gradient term here, and I get something that's the difference between the true gradient and the gradient estimate here. So I've just, in this equation, I've added and subtracted the true gradient. And this delta t now is just the sum of, is just n times eta, right? It's n times the learning rate. I hope that's okay. So now what's going to happen is I've got a sum of random variables. These are random variables with zero mean because this is the expectation of that. And I'm just going to apply the law of large numbers. And the law of large numbers says that when I average a big sum, the distribution of the average becomes Gaussian. So when I take a big sum, the distribution of this I'm going to approximate with a Gaussian. And when you take the sum of these things, the variance of that increases like the square root of the number of things you're adding up. That's the standard law of large numbers says that the mean goes down like 1 over the square root. But if you just took the sum without the mean, it's going up like the square root. So what I'm going to do is I'm going to say, let this be the covariance matrix of these random variables, or the covariance matrix of this zero mean random vector. And I'm going to assume that this thing now can be approximated by a Gaussian. And what I'm going to do is I'm going to take a Gaussian that has zero mean and whose covariance is the covariance of these random variables. And I'm going to take a random vector from this Gaussian and multiply it by the square root of n. And basically what's going on here is the law of large numbers is justifying the transition from this line to this line. Now n is delta t over eta, right? Because delta t is n times eta. So I can replace this n by this expression here, delta t over eta. And I can multiply the eta, this eta in to that square root, and that's going to give me eta times delta t. So this now is, the next parameter vector is a random variable. It's no longer deterministic. It's influenced by this random Gaussian variable. And I can take this square root of eta delta t, and I can move this square root of eta into the random variable epsilon. And I do that by increasing the covariance matrix by a factor of eta. The covariance matrix is like the variance squared. And the quantity of the value is like the variance. So anyway, when I incorporate this eta into this random variable, into the random variable epsilon, I'm drawing from this normal distribution, eta times the covariance matrix. Okay, this equation is written here for a finite delta t. And we've taken the delta t to be large enough and small enough that we've got a reasonable, this is a reasonable approximation of the stochastic update. Now this, what happens in a stochastic differential equation, keep focusing on this equation, is that we can take, under this equation, delta t to 0. So now I'm no longer looking at the finite differencing stochastic differential equation. I'm just looking at this equation. That if I go by delta t, I get a stochastic result that depends on this random variable, but multiplied by the square root of t rather than t. And what happens is you can take this delta t to 0, and it defines a stochastic process. So what is a stochastic process? A stochastic process is a probability distribution over functions of time. So in the limit, as this delta t goes to 0, we get a well-defined time evolution of a probability distribution, a continuous smooth probability distribution over the parameter vector. And this stochastic differential equation is sometimes written this way in terms of a dt rather than a delta t, because we're looking at this limit where delta t goes to 0. And that limit as delta t goes to 0 is defining this stochastic process, right? A probability distribution over functions of time that where this is going to hold for any finite delta t. So this is actually everywhere not differentiable, because this term becomes more and more important as delta t gets, this term dominates this term as delta t goes to 0. Okay, so so just looking at this, at these, oh, and I should have said, this is also related to Gaussian processes. Gaussian processes also, Brownian motion is also an example of a Gaussian process, and that is also a probability distribution over functions of time. So if the gradient was always 0, if we didn't have this term at all, we would get Brownian motion. So Brownian motion corresponds to, you know, what happens to a pollen grain in a liquid. It sort of jitters, and the jittering is happening very fast in time, and you sort of model that as this equation. So that's Brownian motion. If this covariance matrix is the identity function, then we are going to get a Gibbs distribution. But in general, we're not going to have this, that the covariance, remember that's the covariance matrix of the random gradient estimates. And in general, we're not going to have that that's the identity function. But we are going to be able to do some analysis even in that case, where that is not the identity function, identity matrix. Okay, thanks. Now we're going to move on to actually calculating the stationary distributions.